Every night, thousands of ships move through complete darkness. No headlights, no road beneath them, no lanes, no markings, no signals of any kind. Just black water stretching in every direction, and steel vessels the size of skyscrapers moving through it at speed. Some of these ships carry 50,000 tons of cargo. Some stretch 300 meters from bow to stern, moving through the same waters, sometimes toward each other. By every logical rule, this should be a disaster waiting to happen, every single night. But it is not. Collisions at sea are remarkably rare, not because the ocean is empty, not because ships slow down and wait for daylight. They keep moving, through fog, through storms, through the deepest hours of the night, without a single headlight pointed forward. No headlights, no road, no visible lanes. Two ships, both massive, both moving fast, both in total darkness. Why don't they crash? The instinct is to assume ships work the way cars do, that somewhere on the bridge an officer is watching the water ahead, and when something appears, he reacts, he steers, he avoids it. That instinct is wrong. The open ocean gives no reference points, no lanes, no markings, no fixed boundaries of any kind. At night, another ship on the horizon appears as nothing more than a faint point of light, giving no reliable information about size, speed, or direction. It could belong to a small fishing vessel or a 300-meter container ship at full speed. The human eye simply cannot tell. And this is where the assumption breaks down completely. Because even if a captain sees something, even if a light appears on the horizon and the bridge goes on alert, the real question is not whether they saw it. The real question is whether seeing it is even enough. Here is the reality that changes everything. When a car driver sees danger, the car stops within meters, within seconds. A fully loaded container ship operates under completely different laws. When the order goes out to reverse engines, the ship cannot stop immediately. Throwing the engines into reverse at full power risks serious mechanical damage. Engine speed must be reduced gradually before reverse thrust can be applied. And by the time the propeller begins working against the ship's momentum, the vessel has already been moving forward for a significant distance. According to maritime engineering standards, a large ship can require anywhere from 5 to 15 times its own length to come to a complete stop. For a 300-meter vessel, that means continuing to travel between 1.5 to 4.5 kilometers after the stop order is given. The entire process takes 4 to 10 minutes. 4 to 10 minutes. Several kilometers of open water, and the ship is still moving. Now consider two vessels approaching each other. Their combined closing speed can reach 40 knots or more. At that rate, the distance between them collapses faster than any human reaction chain can address. By the time an officer sees the danger, processes it, communicates the order, and waits for the engines to respond, the gap may already be gone. Turning offers no easier escape. When a 300-meter ship executes a turn, the bow begins to swing, but the vessel's mass continues carrying it forward while the turn slowly develops. To complete a 90-degree heading change, that ship advances approximately 1,350 meters in its original direction before the turn is even established. A full turning circle spans roughly 1,500 meters from side to side. That is not a quick escape. That is a ship drawing a massive arc through the ocean while still closing toward whatever it was trying to avoid. Seeing danger is not the same as escaping danger. At sea, by the time something is clearly visible and clearly threatening, the window for a physical response may already have closed. So if a ship cannot stop in time and cannot turn in time, how does it avoid what it cannot escape? The answer has nothing to do with reacting faster. It has everything to do with never being in that position in the first place. But understanding why that system exists requires going back to a time when it did not. For most of maritime history, a ship navigating at night had three tools: a lantern, a compass, and the experience of the man holding them. Different nations operated under different rules. In busy shipping lanes, two captains approaching the same situation could make completely opposite decisions, both following their own country's conventions, both certain they were correct. The result was confusion, and confusion at sea has always had consequences. Then came radar, and for a moment, the maritime world believed the problem was solved. On the night of July 25th, 1956, the Italian ocean liner SS Andrea Doria was crossing the North Atlantic toward New York. The ship carried radar, modern technology for its time. Visibility was poor, reduced by heavy fog, but the officers were watching their screens. The Swedish passenger liner MS Stockholm was heading in the opposite direction, also equipped with radar. Its officers also watching. Both ships saw each other. Both crews made decisions about how to pass, but they read the situation differently, chose different passing plans, and neither communicated with the other to confirm. When the fog finally allowed visual contact, the two ships were less than 2 nautical miles apart, closing at a combined speed of nearly 40 knots. There was no time. The ships collided. 51 people died. Maritime investigators would later describe it as the world's first major radar-assisted collision. Not a collision caused by darkness or missing technology, a collision caused because the technology existed, but a unified system for using it did not. Andrea Doria had radar. Stockholm had radar. Both crews were watching. So what was actually missing? A shared language. Not a language of words, but a language of light. A system so precise and internationally standardized that any trained officer on any vessel anywhere in the world could look at lights on the horizon and immediately understand exactly what they were seeing. That system exists. It begins with 3 colors: red, green, white. Every large ship at sea is required to display navigation lights under the international regulations for preventing collisions at sea, known as coal regs. These are not decorative. Each light carries specific geometric information about the vessel displaying it. The red light sits on the port side, the left side of the ship, shining across an arc of 112.5 degrees. The green light sits on the starboard side, the right covering the same arc on the opposite side. A red light visible means the port side is facing the observer. Green means starboard. Both colors visible simultaneously means the ship is heading directly toward the observer, and that combination demands immediate attention. At the stern, a white light covers the remaining arc of 135 degrees. Only that white light visible means the ship is moving away. Then there are the masthead lights. White lights mounted high on the ship's structure, shining forward across 225 degrees. Ships longer than 50 meters carry 2 of these lights, one positioned higher than the other. The height difference is intentional. The relative positions of those 2 white lights reveal the ship's orientation, whether it is crossing the observer's path, angling toward them, or heading nearly directly at them. The masthead lights on a large vessel must be visible from at least 6 nautical miles. Side lights and stern light from at least 3. A trained officer looking at a single set of colored lights on a dark horizon can determine in seconds which direction the other vessel is traveling, roughly how large it is, and whether their 2 paths create a collision risk. The lights themselves carry the answer. No radio call needed, no guesswork. This is precisely why a powerful forward headlight would not make ships safer. A blinding beam would wash out the coded information navigation lights are designed to communicate. Other officers would see a wall of light instead of a language. The system depends not on illuminating the ocean, but on making each vessel readable to every other vessel around it. Ships do not light up the ocean. They make themselves readable. But this language of light has one limitation. It requires visibility, and sometimes the ocean takes that away entirely. What happens when fog swallows every light on the ocean? When fog closes in, a different layer of the system takes over, one that does not need light at all. Radar sees through fog, through rain, through conditions that reduce human visibility to nothing. A marine radar antenna rotates continuously, sending pulses of microwave energy in every direction. When those pulses strike an object, another vessel, a coastline, an iceberg, a portion reflects back. The return time gives the exact range. The antenna direction gives the bearing. Together, they produce a precise, continuously updating picture of everything surrounding the ship. Under the Safety of Life at Sea Convention, SOLAS, radar is mandatory on all ships above 3,000 gross tons, not optional equipment, a legal requirement. Large ships can be detected at distances of up to 48 nautical miles. A vessel completely invisible to the human eye is already a known presence on the bridge display, but detection is only the beginning. Modern radar systems incorporate ARPA, Automatic Radar Plotting Aid. ARPA tracks every target's movement over time, calculates its speed and course, and automatically determines the closest point of approach, the moment when the two vessels will be nearest to each other if both hold their current paths. It tells the bridge not just that something is out there, but whether that something is a risk. Under Colreg's Rule 7, any vessel with radar is required to use it for long-range scanning, not just close monitoring. The rule exists because of exactly what the physics demonstrated. By the time a threat is close enough to see, it may already be too late to act. And yet, even with all of this, there is something radar cannot do on its own. Radar shows a moving dot, a bearing, a speed, a closest point of approach, but not a name, not a cargo, not a destination. Who is that dot? That dot has a name. Every large commercial vessel on international waters is required by the International Maritime Organization to carry an automatic identification system transponder, AIS. It is not a tracking device installed by outside authority. It is a broadcast system built into the ship itself, and it never stops transmitting. Every 2 to 10 seconds, every AIS-equipped vessel broadcasts its name, exact position, speed, course, navigational status, destination, and cargo to every receiver within range. That range typically extends 20 to 40 nautical miles. Two ships, 40 nautical miles apart, completely invisible to each other, separated by open ocean, are already exchanging information. The bridge of one vessel already knows the name of the other, its speed, its course, what it is carrying, and where it is going. ARPA has already calculated whether their paths will bring them dangerously close. The radar dot is no longer anonymous. It is a known vessel on a known trajectory. Radar shows a target. AIS tells you who that target is. But information, no matter how detailed, does not steer a ship. The system knows where every vessel is. It knows which paths are converging. It can calculate the risk. But someone still has to make the call. All of it. Radar returns, AIS data, navigation lights, bearing calculations, closing speeds, flows to one place, the bridge, and to the officer standing watch. Step onto a ship's bridge at night, and the first thing that strikes most people is the darkness. No overhead lights, screens dimmed, instruments glowing softly. The only working light in the room is red. This is not aesthetic, it is biology. Full dark adaptation, the state in which the human eye can detect faint lights at significant distances, takes 20 to 30 minutes to develop. A single exposure to bright white light destroys it within seconds. The officer standing watch on a dark bridge has spent that time building sensitivity that allows him to detect a faint red or green point miles away on the horizon, a light that would be completely invisible to someone stepping in from a lit corridor. Red instrument lighting exists for one reason. Red wavelengths do not disrupt dark adaptation. An officer can check an instrument and look back out at the dark horizon without losing the sensitivity he spent half an hour building. This officer is not watching and waiting. He is working ahead of the situation. Under Colreg's Rule 8, any action to avoid a collision must be taken in ample time, not at the last moment, not when the threat is close, but early, when there is still enough space for the maneuver to work, given what the physics demand. He monitors radar tracks, watching whether the bearing to another vessel is changing or holding constant. A constant bearing with decreasing range is one of the clearest signals of a collision course. He reads the navigation lights on the horizon, cross-references the AIS data, applies the Colregs to determine who gives way, and acts while there is still room to act. The officer is not guessing. He is calculating. If the ocean looks completely empty at night, it is not. From the bridge, it is something else entirely. Every vessel within range is visible, identified, tracked, and understood. Through any weather, at any distance the systems can reach. Paths are known, risks are calculated. Decisions are made long before any danger becomes something a human eye could see. None of this is accidental. None of it is luck. The question at the beginning of this was simple. No headlights, no road, no lanes. Why don't they crash? The answer is that headlights were never the point. A headlight illuminates what is directly ahead. The system on a modern ship reads the entire ocean around it, miles in every direction, through any weather, at any hour, and acts on that information early enough for the physics to allow it. Ships don't crash without headlights because they were never designed to need them. The dark ocean is not a problem to be lit up. It is a hidden traffic system, and it has been running quietly, invisibly every night, for longer than most people have ever thought to ask why.